Okay, lecture 1.1, systems of linear equations. You should have out your notes by the same name. Definition. A linear equation in the n unknowns, the n variables, x1 through xn, is an equation of the form a1 times x1 plus a2 times x2 plus etc. a sub n times x sub n equals b, where for each I, from 1 to n, a sub I is a known constant, and it's called the coefficient of x sub I, and b is also a known constant. So the unknowns are the x1s through the xn's. Notice, of course, none of them are squared or square rooted, or I'm not taking the sine or the natural log of any of them. It's linear, meaning it's just a constant, a1 times the first variable x1, plus a constant a2 times the next variable x2, etc., all the way up. That's what we mean by a linear equation in the n unknowns x1 through xn. A solution to the above linear equation is an ordered n tuple of numbers s1 through sn, such that if you plug them in, s1 for x1, s2 for x2, etc., you get a true statement, right? The equation gives you a true statement. The set of all such solutions is called the solution set of the linear equation. This should not be real shocking to you. But I give you an example here. 4x1 plus 3x2 equals 12 is a linear equation with an infinite solution set. And of course, we can represent the solution by a line in the x1, x2 number plane, or the xy number plane, if you like. Let me see. Let me keep it down here, kind of low. So let's call this the x1 axis, and we'll call this the x2 axis. We could say x and y, but then when we go to 3 variables, we'd have to have x, y, and z. When we go to 4 variables, what, w, x, y, z? We eventually, at some point, if we're going to have 10 variables, we just want to label them x with a subscript, x1, x2, x3, etc. All right, so x1, x2, and it's real easy to figure out. I got an x2 intercept up here at 4, and I got an x1 intercept at 3, I do believe. And what I get this line. The line means the whole set of ordered pairs that give me the points on the line are ordered pairs that solve the equation. So that one works. 3, 0 works. Plug it in. 4 times 3 plus 3 times 0, that's 12. 0, 4 works. 4 times 0 plus 3 times 4, that's 12. There's another one here, what I think I have like a 3 halves. You go up to 2 maybe. And I think that one works, doesn't it? 4 times 3 halves is 6, plus 3 times 2 is 6. Yeah, that's 12. Okay, etc. So all the points along here represent all the solutions. So we have an infinite solution set, which should not be surprising to you. Okay, I have a definition here. A system of linear equations in the n unknowns is a set of one or more linear equations, as we've seen. The solution set of the system is the set of ordered n tuples, each of which is the solution for each equation in the system. We will learn that there are 3 possibilities for a solution set for a linear system. Either there's no solution, it's empty, the system has no solution, it's an empty set, or it contains exactly one ordered pair or ordered triple or ordered n tuple, however many variables you have, or it contains infinitely many n tuples. So there are 3 possibilities. We will see this. No solution, exactly one solution, or infinitely many solutions. No solution, we say a solution doesn't exist. One or infinitely many, we say that there is a solution, it exists, and in the case of one, we say it is unique. That means one of a kind, right? And it's non-unique if there are infinitely many, obviously. All right, and I have an example here that you should be filling this out as we go, right? Let's see. So I guess let me put it about right, maybe about right here. I have a system, x1 plus x2 equals 3. So there's one equation in the 2 unknowns, x1 and x2, and I'll give you another one. x1 minus x2 equals, what do I have? 1. So please put this down. All right, if we graph this, these two equations, x1 plus x2 equals 3, that's going to have a y-intercept, or I should say an x2 intercept of 3 and an x1 intercept of 3, so I get that line, essentially. And what does x1 minus x2 equal to 1 look like? Well, it goes through the, let's see here, it's going through the x1 axis at 1, goes through the x2 axis at -1, and I get all of those ordered pairs, right? So the solution set here is this line. The solution set here is all of this line, all the points on that line. So look, in fact, I have a solution where both equations are satisfied. And of course, geometrically, that's the intersection of the 2 points. We say that the system is consistent. One ordered pair satisfies both equations, satisfies all the equations in the system, right? All right, well, let's do another example over here. How about x1 plus x2 equals 3? Excuse me, so I have the same thing that I had before for the first one. I have that line, and that's intersecting at 3. And suppose I have, I have x1 plus x2 equals 1. Well, look, those are parallel lines, right? And the one has a y-intercept, or x2 intercept of 1, whereas the other one has an x2 intercept of 3. So I have these two parallel lines, right? There's no intersection. We'd say this is an inconsistent system. And I just say no ordered pair, no ordered two-tuple, no ordered pair satisfies both. Okay, so I have here an example of non-existence of a solution. Over here, I have an example of existence of a unique solution. It's just that one. I'm not going to do an example right now of existence where we have infinitely many solutions for a system, but you know what's going to happen, right? What's going to happen is the second line here would be parallel to the first, but would have the same y-intercept. It would sit right on top of it, right? They'd be the same line. That's how I'd get infinitely many solutions. So I'm not going to do that example. Yeah, so let's see here. I think I'm ready to say, yeah, as I'm rubbing this out, the next definition is two systems of linear equations are said to be equivalent if they have the same solution set. They do not have to have the same equations in them, but it has to be that their solution sets are the same set. All right. And I have, I think, two examples of that. Don't worry, this won't fall apart. It sounds like it's about to come crashing down. It's not. At least it hasn't yet. Yeah, example. The two systems below have the same solution set. So what do I have here? I have the one I just had. I guess I'll put it about right here. x1 plus x3 equals 3, and x1 minus x2 equals 1. I could have left that one up, but I'm rubbing them out. I'm redrawing them because, of course, you have to redraw them in the different space you have there to do this. So I have, again, at 3 and at 3, I get that, and I get that, and then at 1 and at -1, I get that, and this turned out to be the point, what was it? It was 2, 1, right? Yeah, it was the point, I don't even know if I said that last time, right? But it has the single point 2, 1 that solves them both, right? 2 plus 1 is 3, and 2 minus 1 is 1. There we go. All right, I want to compare that with the system. What do I have as the second system? I have x1 plus x2 equals 3, and then I just have x2 equals 1. All right? So what does that look like? This is a legitimate equation, right? I have 0 times x1 plus 1 times x2. So that's a legitimate equation in the variables x1, x2. I just don't have x1 occurring explicitly. The first one, of course, is there. So that line is the same. But the next line, x2 equals 1, that's going to be about right there, right? It's just this horizontal line. Sorry for the family of mice living here squeaking. So I have a different system. Geometrically, it's different, but I have the same solution set, right? Solution set is the same for both. So these are equivalent. Right, they're equivalent systems, and I guess what do I say next? I say it's easier to see the solution from the system on the right, isn't it? Because I can just immediately see, well, x2 is 1, and then I can plug back in and figure out that x1 is 2. So much of what we will do in this class will, let me see, I want to keep these up. I think I'm going to rub them out and see what's the next slide here. Yeah, it's easier to see that I can learn from this one more quickly what the solution is than from this one. Right? So much, let me rub this out so you can read it. Much of what we will do in this class will amount to replacing a system of linear equations with an equivalent system, one that has the same solution set, from which it is easier to read what that solution set is. Okay? Doesn't that make sense? I give you a system that I don't understand the solution set for, but if I can convert the system into one where it's easy to read the solution set, and it's the same solution set, it's an equivalent system, then I'm working. So how will we do this? Well, we'll employ some simple algebra to eliminate unknowns from some of the equations until we have an equivalent system where it's easy to find the solution set. And you've done this many times. You've had 2 equations and 2 unknowns. You know, you add a multiple of one equation to the other to eliminate a variable and make it easier to solve, all right? So we'll do this in a very systematic way in this class. We're going to use some of the ideas that you know, but we're going to make it very systematic. We'll put the given system on what we call triangular form, and then we will use back substitution. What does triangular form mean? What does back substitution mean? You might already have an idea what it means. If not, I'm going to do a couple examples and it'll be real clear. Okay, so consider the previous 2 systems. So what I have then is right here. I have the first one was x1 plus x3 equals 3, and then x1 minus, sorry, not x3, when I have x3. Think of a 3, I guess. x1 plus x2 equals 3, and then x1 minus x2 equals 1. And if you look at that, if I add that to that, those go away, and I just have an equation in x1. So that's a simple way to do it. But that's not the way I'm going to do it. I'm going to do it, like I said, in a very systematic way. What I am going to do is I am going to, with the variables set up like this, where I have x1 in line with x1 and x2 in line with x2, I am going to use this equation to eliminate the x1 there. So what I'm going to do is I'm going to multiply the top equation by -1 and add it to the bottom equation. So I'm going to keep this the same. And this one, I'm going to add, or I should say, yeah, I'm going to add negative of first equation. Don't worry, we're going to have a better way to write all this, but just right now, I'm just going to give you kind of the intuition. So I take a -1 all the way through here, and that makes this a negative x1. If I add it there, it's gone. right? There's nothing. And I have a negative x2, and if I add it there, I get a negative 2x2 equals, and of course, if I do that to all the way across, I get a negative 3 here, and added down there is a negative 2. Now, what are we doing? The first thing I'm doing is I'm multiplying both sides of an equation by the same non-zero number. You all know that that's okay to do. It keeps the equation balanced. Then what? I'm taking this equation, and I'm going to add the same thing to both sides. Right? If I add the same thing to both sides, it still has the same solution set, that equation. What am I adding? On the left side, I'm adding the negative of this, and on the right side, I'm adding the negative of that. But they're already the same, so because it says they're equal, right? So if I add it, I'm adding the same thing to both sides, and I get this. Okay, look at what I have here. Now, this is very, let's see, where is it? Okay, yeah, okay. I'm just going to tell you right now, what I've done is I've cut off that variable here, right? So I've created a little triangle where there's nothing, right? We call this the triangular form for the system, or a triangular form for the system. So now all I need to do is back substitution. All right, so in the case of two equations with two variables, getting it in triangular form means knocking out the first variable in the second equation so that I have an empty triangle right here. And now what does back substitution mean? It means start with that bottom equation and solve for the variable that's sitting there. So I divide by negative 2 and I get x2 equal 1. Now, go up to the first equation and substitute x2 equal 1 in. So now, sub x2 equal 1 into first equation. So I'm going backwards, right? I'm going upwards. So I have x1 plus what's x2? 1 equals 3, and easily I can solve and get x1 equal 2. So that's how I get my solutions algebraically. And like I said, I don't want to belabor this because you've done it all a million times, but I do want to point out that we're doing something kind of specific. I have a very specific way of doing it to get that triangle there, and I have a very specific way, once I got that, to go backwards to sub all the way through. Let's do a little more involved example. Let's see, whoops, sorry, here we go. Okay, so what you ought to do is see if you can pause me and do this problem. Now, I haven't told you what triangular form means in this case where we have three equations with three variables, but you can about figure it out, I bet. If you can't, don't worry, I'm going to work through it. I don't have a way to just click a clicker here and have all this stuff get erased. So I guess you can skip. Assume that I won't, while I'm erasing, say any gems of wisdom that you will miss. All right, let's do that one. I dropped my marker, so we'll use a different color. All right, so I guess I have here. So first off, it's a little bit of a mess, right? Excuse me. If I want to use multiples of one equation to eliminate variables in the other, I want the variables all lined up. So that's the first thing to notice. I got an x1 minus the constant term. 1 is on the left-hand side, and then I got a 3x3 before I get to the x2 term, right? And then it's equal 0. It's okay. They're all kind of messed up. So let's rewrite the very first one. The very first one should be x1. Sorry, my head's in the way. Then what? Plus 2x2. And then plus 3x3 equals, and that'll become a positive 1 when I throw it to the other side, right? Then it looks like I have a 2x1 plus a 6x2 plus a 10x3, and that equals 2. And then what I have, an x1 is on the right-hand side right there, right? I got to put it over there, so I'm negating it. So it's a negative x1. And the same thing with the x2. It's a negative x2. and then I have a 5x3, and then that 11 minus 11, when I throw it the other side, add it to both sides, I get 11. Okay, now what I'm going to do is this time I'm going to get this in triangular form, and what that's going to mean is, of course, I want this to be an empty triangle. Makes sense? I will get rid of the x1 term here, and then I'll get rid of the x2 term here. Then look what I'll have. I'll just have an equation that involves x3, and I can solve for it. I can plug it back up in here, and then I'll just have an equation that involves x2. I can solve for it. Then I'll back sub up here with x2 and x3, and the equation will just involve x1, and I can solve for x1. All right, so what am I going to do? I'm going to be, and did I write this out in detail? I did not write it out here. I'm just going to say it. I am going to take this equation. I have to write, at each stage, this is important, at each stage I need to write an equivalent system. All right? At each stage it needs to be an equivalent system. So I want to keep 3 equations. So this thing was squeaking. Let me try this and see if it doesn't squeak so much. So my first rewrite of the system will be that I keep my first equation the same. All right? Then what I want to do is I want to change this, so I want to add the same thing to both sides. That wipes that out. What I'm going to do is I'm going to take all of this times -2 and add it down. So can we just do that step by step? I'm going to take a -2 times x1 and add it to there, so it's gone. Then I take a -2 times 2x2, I get -4x2. Add there, I get 2x2. And then I take a -2 times 3, x3, and it's -6x3, add it to there, I get plus 4x3, equals, then I take a -2 times 1, -2, add it to there, I get 0. All right? Now look, I just need to take the top one as is and add it straight down, right? And that'll wipe out that x1. So if I add it straight down, they're gone, and a 2x2 and a -x2 just gives me an x2. A 3x3 and a 5x3 gives me a positive 8x3, and if I add down, I get a 12. Okay, now I recommend a couple of things here I can do, and I guess I need to eliminate the x2 there, but I think what I'm going to do is I'm going to, maybe not go quite so high, I don't need to go so high. I'm going to rewrite the system where I keep the first equation the same. And I think what I'm going to do is I'm going to flip and put the third equation in the second place. Clearly, that doesn't really do anything bad, right? It keeps x2 plus 8x3 equals 12. It keeps everything the same. Okay, and why did I do that? Just because now I can take this equation times -2 and add it down and wipe it out. I could have come over here and taken this equation times -1/2 and added down, right? And that would have been just fine. It would have wiped out the x2 there. But I just did this to show that it doesn't hurt to just reorder the equations, right? That little move will become useful later. So now let's take I think what will be the final step of messing with the systems. x1 plus 2x2 plus 3x3 equals 1. That stayed the same. I'm going to leave x2 plus 8x3 equals 12 the same. And now I'm going to take this times -2 and add it down. And when I do that, the x2s are gone. -2 times 8x3 is -16x3 plus 4 is -12x3 equals -2 times 12 is -24 plus 0 is -24. Terrific. I have an empty triangle there where I've knocked out all the x1s here and then the x2 here. And I'm ready to back solve. So -12x3 equals -24. Divide through and get x3 equals 2. Plug that in up here to the second equation. x2 plus 8 times x3, but x3 is 2. That's equal to 12. So I have x2 plus 16 equals 12. x2 equals -4. Great. One more thing, I have my first equation here, is right here. So x1 plus, now back solve these and these in here. So 2 times negative 4 plus 3 times 2 equals, that equals 1, right? And I think I have room to do it here. x1, that'll be minus 8 plus 6 equals 1. I'm about out of room. So what, x minus 8 plus 6, that's x minus 2 equals 1. So I lost my, it's x1, right? x1 minus 8 plus 6 equals 1. So x1 minus 2 equals 1. So x1 equals 3. There I go. I have, again, a unique solution, right? It is the ordered triple x1, x2, x3 of 3, comma, negative 4, comma 2, right? And if you've had Calc 3, you know that these three equations each represent a plane in XYZ space, or in this case, x1, x2, x3 space, so in three-dimensional space. So what do we have? We have two planes coming together like this, so their intersection is a line, and then we have a third one coming in like that, and their intersection is then that point where all three come together, and that's what we found, right? If you've had Calc 3, this should, you should kind of have a geometric image of what's going on there. Okay, great, but that's how we put a system in triangular form and do back substitution to solve. But you should notice something here. I'll rub a little out here. It's kind of a lot of writing. It's a lot of writing, and I'm dragging along these x1s and x2s and x3s all along, when really, isn't it true that just the columns that they're in tell me what kind of variable they have? So that suggests something, that maybe there's an easier way to do this. And the easier way to do this is to use what we call matrices. An m by n matrix is a rectangular array of numbers orderly arranged in m rows and n columns. Let's see. I'm rubbing so that you can read it. Does it say? Read slowly. It says that the coefficient matrix for a system of linear equations is the matrix obtained by extracting the coefficients of the variables and putting them in a matrix in the natural, obvious way, right? The ith row of the matrix will be the coefficients that are in the ith equation, and the jth column will be the coefficients for x sub j throughout all the equations, right? That's what we mean by the coefficient matrix. It's a matrix of coefficients. Well, if we add one more column, we have the augmented matrix. It is the coefficient matrix where we've just added an extra rightmost column, and that's got the right-hand side of the equation, right? All the things that we set everything equal to, right? In the most obvious natural manner, you stick them on at the end. All right, so if you go back and look, I didn't rewrite the system. I couldn't leave it up there because we had writing going over it. But if you look at that system, there's the coefficient matrix, and the augmented matrix is right there. So let's just put the augmented matrix in triangular form. All right, so let me just start here with 1, 2, 3, 1. Now what I'm going to do is I'm going to take negative 2 times this row and add it to that row, right? So that gives me 0, 2, 4, 0. And then I'm just going to take the top row, well, I guess right here, top row here, and add it to the bottom row. So I get 0, 1, 8, and 12. Then what? I'm going to keep that top row the same, and I could interswitch. I guess I'll do what I did in the original. I interswitched the equation, so I'm going to interchange the rows there. Okay, so that's my next step. Then what? Then I'm going to I'll keep the Top row the same, and I'll take this times -2 and add it down. So this, of course, stays the same. And I get 0, 0, -12, and -24. Okay, and now we do back substitution, right, as before. I'm not going to run through that. But look, now you can see what having a matrix in triangular form means. It means you have this lower triangle of zeros. That's the way we want to think of a system being in triangular form. Means its augmented matrix has been put in a form where you have this lower triangle of zeros. Once you have that, boom, 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 you can do back substitution, right, to get back to where you were. Okay, so I'm not going to, again, do the back substitution there, but this is the way we want to start thinking. We want to think in terms of matrices. I want to think of getting them in triangular form, which means have that lower triangle of zeros. And let's see if I have room. Yes. Given a matrix M, a row operation on M is one of the following procedures. What we want is we want to have a way of converting a system into an equivalent system with this, but it's easy to read the solutions off by doing back substitution, right? So we're going to put it into an augmented matrix form. Excuse me. Then the sorts of things that we were doing with the system, adding a multiple of 1, switching them around, whatever, we want to do those with the matrix, right? The corresponding matrix. We don't have to write x1, x2, x3 every time. We're just manipulating the matrix of numbers because the first column is going to be the x1 column, the next column is going to be the x2 column, et cetera, just like we did here. So what I want is I want to then kind of codify and lay out the procedures that I have for manipulating a matrix to put the augmented matrix into an equivalent form. So the first thing we can do is we can interchange one row with another row, all right? And I did that here, right, where I had right above here, I had these switched around. I just switched them around, right? And of course, that corresponds to switching the order of two equations in a system which clearly doesn't change the solution. The second thing we can do is we can multiply one row by a non-zero constant. All right, isn't that saying I'm multiplying both sides of an equation by that non-zero constant? Right, as long as I'm dealing with the augmented matrix where it has all the coefficients and the right-hand side, if I multiply the whole row by the same constant, I'm multiplying both sides of the equation by that constant. I'm not changing the solution set. So this should be a valid thing we want to allow ourselves to do. And the addition of a multiple of one row of M to another row of M. I've been doing that all along, and that's like taking a multiple of one equation and adding it to another. So all of these things are done to an augmented matrix, are not going to change the solution set. So these are what we're going to mean by row operations, and we're going to use row operations. So what do I say here? It should be obvious that if we perform any of these row operations on the augmented matrix of a system of linear equations, we will arrive at the augmented matrix of an equivalent system. Equivalent meaning has the same solution set, which is what we're after. We're after that solution set. So to find the solution set of a system of linear equations, here's the big thing. Use row operations to put the augmented matrix into triangular form and then use back substitution, which is what I've already been saying. But that, in a nutshell, right here is what we're going to do. All right, so I have a couple examples here. And first one is, so solve, and that means find the solution set of this system. And that's what I mean when we say solve, find the solution set, right? Well, okay, let's, what do I say here? I think I say the solution is, hey, pause and work it out. You really should pause me and see if you can do this one. Write down the augmented matrix. Do your row operations. Get it in triangular form. Back solve and get an answer. So please stop me and do that. Okay, off we go. Let's see if what you got is what I get. All right, so there's the augmented matrix, of course, 2, 22, 7, 22, right? Just peeling off the coefficients on the right-hand side. And then 2, 19, 0, 11, right? There's no x3 here, which means its coefficient is 0, right there. And then 1, 8, negative 3, 1. All right. Now, what I'm going to do is I'm going to show you a kind of a bookkeeping way that I like that make sure I'm doing things right, because it's very easy to make one little calculation wrong, and if you do that, sometimes you can't go back and figure out where you were, right? So here's the augmented matrix where I've labeled the rows, R1, R2, R3 for row 1, row 2, row 3. Okay, what I want to do, just because it looks like it'd make things easier, I could divide this row by 2, right? So I get a 1 there, right? Because then I can use that to get a 0 there and a 0 there, which is what I'm after. Or I could just leave it as a 2, and when I need to down here, multiply this by a -1/2 or something. I'm going to divide by 2 at some point if I keep this row here, but then I got this 7/2, and I'm already messing with fractions. I can do that, nothing wrong with that, but it starts to get easier to make errors, right, once you're dealing with fractions, and it gets a little messier. So why don't I use the row operation, the very first one, which says I can switch and put row 1 down where row 3 was, and row 3 up where row 1 was. And then I have a 1 there, right? That seems to me to be the easiest thing to do. Now, with the 1 there, I'm going to use multiples of this row to get a 0 there and a 0 there, right? So what do? Well, first, let me back up and say, look at how I've bookkeeped that. I took row 3 and I made it the new row 1. I left row 2 alone. I took row 1 and I made it the new row 3. So that's kind of like how I like to do that. Now look, so row 1 stays as is, as row 1, but then I'm going to take -2 times row 1 and add it to row 2, and that becomes the new row 2. And when I do that, see that, in fact, I do get -2 times 1 is -2, add there, 0. -2 times 8 is -16, add there is going to be 3, which is what I have, right? And then -2 times -3 is +6, add to 0, you get 6. -2 times 1 is -2, add to 11, you get 9. Similarly, I get the bottom row. You should be able to see that. -2 times row 1 plus row 3, and that's the new row 3. What's left to do? Why don't I use this row to get a 0 right there? So I'm going to take row 1 and row 2 stay alone, and stay the same, and then I'm going to take -2 times row 2, add it to row 3. That's the new row 3. And looky there, I have a system, right? I can see that. I can do back substitution and see that x3 is 2, right? And 3x2 plus 6x3, which is 6 times 2, that's 9. So I have 3x2 plus 12 equals 9. 3x2 equals -3. x2 equals -1, so I have x3 is 2, x2 is -1, back substitute all the way to the top. That top row, you should get used to being able to read. That means x1 plus 8x2 minus 3x3, right, equals 1. So I have x1 plus 8 times x2, which is 8 times -1, plus or minus, so plus a -3 times x3, which is 2. That's equal to 1. So I think I have x1 minus 8 minus 6 equals 1. That's minus 14. So when I add, I think I get x1 equal 15. Right? So again, I get a unique solution. These 3 planes are intersecting in exactly 1 point. Okay, great. Another example. Here's one. It's 4 equations and 4 unknowns, which clearly I'm going to get, it can get pretty nasty, right? If we have 10 equations and 10 unknowns, you're going to want to use technology to solve that. But this one, I say here, something interesting happens. And I'm about to do it here, but think about what we expect to have come out of here. What will a lower triangle of zeros be this time? Putting it in triangular form, isn't that going to mean the matrix will have a 0, then a 0, 0, then a 0, 0, 0, right? So we'll have a lower triangle of zeros, right? And I'll have the top equation there, and then there's the next equation, there's the next one, and then here's the last. And I'll be able to, this last one I can solve for whatever that number is and just back substitute, right? That's the, would be the general idea here, right? That would be what we're trying to do, and I believe that y'all can do it. But you should pause again and try to do this one. And I say something interesting happens. So let's go forward and see what the interesting thing is that happens. Excuse me. So I have 1, 2, 1, negative 1, 5. Then I have 1, 3, negative 7, 2, 6. Then I have a negative 1, a negative 1, a negative 7 again, and a 3 and a 2, and then I have a 1 and a 2 and a 3 and a negative 2 and a 12. I got those right. 1, 2, 3, negative 2, 12. Okay, there is my initial augmented matrix. It's pretty quick to just do multiples of this down there to get zeros there, so I get my column of zeros started there. So let's see, I think I can fit that in here, and I'll use a different color. Yeah, I can get that in here. So I'll keep this row the same. 1, 2, 1, negative 1, 5. And I'm going to add negative 1 times this onto there. And I'm not going to write it out here. I'm not going to take the time to do that. I like it if you do that, actually. Like I said, it keeps your bookkeeping honest, and it helps me if I'm grading sometimes to see if you make an error. I can't tell what you did, but if I say, oh yeah, I see they did the right thing, but they had one little calculation wrong. So if you write down what you do over here, that I want you to do that, but I'm going to not do it just to save time. So I take negative 1 times this and add it down. So when I add there, I'll get a 0. When I add there, I'll get a 1. When I add there, I guess I'll get a negative 8. That's going to be a positive 1 plus 2 is 3, and a negative 5 plus 6 is 1. Now I'm just going to add it straight down to there, right? So I'm going to get a 0 and a 1 and a negative 6, right? And a 2, and a 5 plus 2 is a 7. And I'm again going to take a negative 1 times this and add it all the way down to the bottom. So that becomes a 0, and that becomes a 0, and that becomes a 2, and that becomes a 1 minus 2 is a negative 1, and this becomes a negative 5 plus 12 is a 7. All right. What is left to do? I got zeros here. I already got a 0 there. How about that? I'm going to use the second row to get a 0 there, and I would use it to get a 0 there, but I already got one, so I just got to go there. All right, so come here, and first row stays the same. 1, 2, 1, negative 1, 5. Second row stays the same. 0, 1, negative 8, 3, 1. Third row, I'm going to take negative 1 times that and add it down. So I'm going to get 0. The nice thing about this, of course, is I don't mess up that 0, right? Because what I'm multiplying by, the negative 1 by, is 0 here. When I add it, it doesn't change it. So that stays 0. And now I get a 0 there. Negative 1 added onto here, times here, is a positive 8 minus 6 is a positive 2. This is a negative 3 plus 2 is a negative 1. This is a negative 1 times 1 is negative 1 plus 7 is 6, right? And the bottom row I'll keep the same because it already had lost its 0 there. To finish out, I need just to get a 0 there, right? So let's do it. 1, 2, 1, negative 1, 5, 0, 1, negative 8, 3, 1, 0, 0, 2, negative 1, 6. Finally, I'll take negative 2 times this row and add it down. Negative 1 times this row and add it down, and that'll wipe that out, right? So I have my 0, I have my 0. This will give me a 0. But look, negative 1 times negative 1 is positive 1 added there is a 0. We got a 0, a bonus 0. That's okay. There's nothing wrong with that. We got an extra 0. But hey, here's our lower triangle of zeros that we were after. Okay, but now what happens here? I negate there and I get a 1. Okay. We're done putting it in triangular form. We got, like I said, a bonus 0, which is no big deal. That's just fine. But when we go to back solve, we see that there is a problem. Here's my x1 column, here's my x2 column, here's my x3 column, here's my x4 column. So this says that 0 times x4 equals 1, so 0 equals 1. No, all right? I see this system, the system that has this augmented matrix, cannot have a solution because I've arrived at a false equation, right? If it has a solution, 0 would equal 1. But the solution set here, since this is equivalent to that, I got from here to here just by doing row operations. We have a nice equivalent system. Since this solution set doesn't exist, the original solution set doesn't exist. So no solution. Solution set empty. Solution set equals the null set, right? Okay, so that can happen. We're in four-dimensional space here. We have what we would call hyperplanes. They do not all intersect in even just one point, all right? They don't all intersect together anywhere. There is no solution. So we have a non-existence situation here. Okay, and I think I mentioned that's where we're stopping here, but just to say one more thing, we have two fundamental questions about a system of linear equations. All right, now what are those? I hope you have filled out everything, as we've gone through, and like I said, pause me and work them through on your own when you can. So, right here at the end now, a little bit more to fill in. What are the two questions? Number one, does, like that, try this, does a solution exist? All right? Maybe, maybe not. We see here that sometimes it doesn't. You already had the example way back with the two parallel lines. No solution exists. So this is what we call an existence question, right? Does a solution exist? If a solution exists, is there only one solution? All right? So up here, we have what we call the existence question. Does a solution exist? If it does, we have what we call the uniqueness question. Is the solution unique? Unique means one of a kind, right? Unique doesn't mean unusual. It means one of a kind. So, as I already told you, what we're going to see is that we have three possibilities. Either means either or, so it's three possibilities. Solution doesn't exist, or it exists, and if it does, the solution is unique, or if it has more than one solution, it's not unique, it has infinitely many solutions. And we'll see that in later lectures. But I'm getting done in less than 50 minutes, so there you go. I will stop here.